And away we go. So pattern recognition, the point of this slide is that pattern recognition is one of the, as it says here, sort of four main areas. Of course, there are others of computational thinking. Now, I hope you can get from the diagram there that pattern recognition partly is about seeing things that are repeated. Because if we see something that's repeated, that's easy to implement in a computer program. We can do things called loops, and you can see that in this algorithm here, where we get to a point and then we go back and repeat a command. So that's what we can be looking for. Pattern recognition is not only for computing people. It's also it's a skill used by a lot of mathematicians, of course. But anybody who wants to do something in a systematic, structured way would benefit from pattern recognition. I don't know if you guys have ever heard the concept of IQ test. You may have even done one sometime, right? You can find them online. If you attempt an IQ test, many of the questions will be pattern recognition. I mean, that's what they do, right? Can you recognize a pattern? And the patterns will be, some of them will be visual sort of symbols, and some of them will be numbers. And so that's a big part of it. I mean, if you want to get a higher score on an IQ test, you think, oh yeah, I'd like to. Well, you can sort of practice your pattern recognition, I think might help. If you realize that that's the kind of questions they got, then, you know, as opposed to just going in there, oh, what's that, right? And so you can see that here, right? We can see patterns. I don't know why this is showing up there. Maybe if I hit that button. Yeah, okay, well, it's smaller still. All right. You see a pattern here from a very simple pattern where we're just adding 4 to each number. Each number is the same as the number before it with 4 added to it. And then we get the next one, which is kind of also similar. It's just the number before multiplied by 3. And then the next one, which is actually kind of a famous one, it's missing out the first number in the sequence. First number in the sequence should be a 0, but then this forms a thing called a Fibonacci series. And how that works, so if you can imagine the 0 being the first number there, but how that works is that the number is equal to the 2 numbers before it added together. So the 2 is equal to the 1 plus 1, the 3 is equal to the 1 plus 2, the 5 is equal to the 3 plus 2. Get the idea? The 8 is equal to the 5 plus 3. So the number is equal to the 2 values before it added together. That's a Fibonacci series. And it's famous because we use Fibonacci series as an introduction. It's famous in computing and in mathematics. But the Fibonacci series is famous in computing because we use it as an introduction to the concept of recursion. So I'm not going to teach you recursion in this course, but you will see it within the next year, I'm sure. And so think back, oh yeah, Fibonacci, that's probably going to show up as recursion, because think about it, you can make that problem fairly simple, right? Look like a big problem, but it's pretty simple. It's just take the 2 values before this value and add them together. And then the result of that is this value. And you can just keep repeating that over and over again. And yeah, that's Fibonacci. So there's a pattern here also. So as I said, recognizing patterns could be some visual pattern or could be some numeric pattern. Here's a pattern. If you worked in a, if you went to work in an office and you're working with receipts, probably the first couple of days, maybe your accounts receivable or accounts payable in the office. First couple of days, you'd be looking at these receipts and you'd be like, oh, what's this, right? Maybe you're reading every word and looking at it. After a while, you'd recognize the pattern of the receipt. You'd know where everything on that receipt was, and you'd know where the information that was important to you was, and you could read the receipts really fast. You could go through and say, oh yeah, I see. This is what maybe you're interested in the handling, or maybe you're interested in the, in particular units on the receipt, or maybe you're interested in the tax or whatever. But at first you'd have to sort of find your way there, but then you'd recognize the pattern and you get pretty fast at it. We find is work like that, that's repetitive. Pattern recognition eventually comes and then it becomes a lot faster. Right, so that's a very important thing in computational thinking. It does make our programming easier. It allows us to do things like I've mentioned, iteration, repeats. We can put repeats into our computer code. So that's something that requires you to recognize a pattern before you can do that. Another thing that you can do is you can have an entire module, which you know is going to be used maybe again in this program, or maybe could be used by somebody else. So you recognize something that happens a lot. Then you create that as a module, and that can be reused. This is also part of the concept that we call software engineering. So the idea of software engineering is to introduce the concepts that apply in engineering generally to developing software. And some of those concepts are things like reusable code. And so modules, decomposition and reusable code. So we've got two different problems here, right? So an athlete throws a discus. Discus is like a weighted disc, and wants to get the average. They're doing that 3 times. A meteorologist wants the average temperature. What they're doing is they're measuring every hour the temperature over an entire year, and they want to find out the yearly average temperature. Now, the only difference between those two problems is the actual scale. And what I mean by that is how many measurements you're making. In the first one, we're only making 3 measurements. In the second one, we're making, well, 24 hours in a day. So 24 measurements every day, 365 days in a year. So 24 times 365. I haven't got that off the top of my head, but you know, it's going to be a couple of thousand, it's going to be 5,000 something, right? It's going to be a lot of measurements. So the difference is big in the number of times it's happening, but what's actually happening is not that much, right? We take all of those measurements, we add them to a total, and then we divide the total by the number of measurements. That's something that a computer could do very well. And so that's a scalable problem, and it's ideal. What I just did, and I hope that you followed that okay, and probably maybe you were even ahead of me on it, is the pattern recognition, recognizing that they're actually the same problem, even though, okay, this one is only 3 measurements and this one is 5,000 something measurements. They're actually the same problem, but one is just repeated more times. Okay, so yeah. When you start using the code.org, you'll see a lot of repeat there, because what it is you've got this little bird. The first little module is using Angry Birds, and you got this little bird that you have to move around. And so repeat is very helpful for that. And I'll show you that maybe today. Okay, so assume that you have a program that draws polygons. So polygons have a number of sides. Angles are between consecutive sides. They all need to have a color and a position to draw them. They occupy an area on the screen. So you could create a program that would work with that. You'd have to enter as inputs into the program what are the angles and the distances. You could do that with vectors for the angles, I suppose. And distances are easy to measure. You could create a program that would do that. In fact, there are many programs that sort of work like that. And actually, your Angry Birds will kind of work like that. This is kind of more modern computing. This is really the last 10 years. It is real. You can identify a cat by the particular components there. You know, how the eyes are related to the nose and the shape of the nose, etc. You could look at that. A computer system could probably identify that as a cat. Also, in a crowd, you could identify human faces. You'll know that that's true because when you take photos on your smartphone, the photo managing software is putting a little square around people and saying, you know, who's this, who's that? And if it's somebody that you've taken photos of many times, it'll actually offer you the name, right? You know, this is you, this is your friend, you know. And so that makes that easy. Now you see in the diagram in the bottom right-hand corner, all of the dots. So that I'm not sure of that exact algorithm, but the idea behind it is that each of us has a unique distance between certain places on our face, right? So if you measured from one corner of my eye to the other corner of the other eye, and then the insides to the eye and other places on my face, and took all of those measurements, they would be different than if I measured it for you, or even if I measured it for somebody else. So even like I've grown this beard, which I didn't used to have, but even with that, a software thing should be able to identify that's me just by these measurements that they're doing there, right? Now, ideally, they get as many measurements as they could, so they would like you not to have the beard or the face mask or whatever. But and so they might ask you to remove that. But generally speaking, they can kind of sort of tell that. And you know that again with your smartphone, this technology has come to us as consumers, isn't it? Right? You can use your facial recognition as a key to unlock your device, just like you can use your thumbprint. And that's how they're doing it. They're measuring different points within it. And that's the end of that set of slides. So the idea there, pattern recognition, we see it from the very sort of simple thing of building up small algorithms, particularly with repeats in them, or what we call iteration, right up to our very powerful computing that we have in things like facial recognition, which is again recognizing a pattern. That's very modern, as I said. Now I want to just go back, because that only took a couple minutes. I'm still recording, so I'm not going to stop recording, but I'm just going to go back. And this lecture I gave to you before, but one of the other teachers had a crack at it and did a bit of a added a few things to it. So look at this as a review with some enhancement. Okay, so right. Oh. Slideshow, yeah, show me the slideshow. Oh, there we go. All right, so do you remember? We were talking about, this goes back to the first slide we had in the last slide deck, which is that we have different components, different things that make up computational thinking. Of those, one of those is abstraction. And so let's focus on abstraction for a little bit here. Abstraction is a way of expressing an idea in a specific context. Do you notice the important word there? We're suppressing irrelevant details. Another way of saying that is that we only look at the stuff that we're interested in. We get rid of, or we obscure. They use the word it's suppressing. We obscure, we hide. Maybe that's an easier word, which kind of means the same thing in this context. We hide the things that we're not interested in. So I'm not sure what the purpose of the, it's a model. Yeah, okay. So I don't know if you're aware what that model is. That's actually a model of, oh, it looks like a periodic table, but if you look at it here, it's got action, sequence, decision, iteration, list, dictionary, type, and property. And so we're using the, what if you just had a single line for action? Or what if you just used AC for action? Or what if you used just SE for sequence, I guess. Decisions, a point with two arrows coming out of it. We see that on our diagrams. Iteration as a loop. I have to admit, when I first look at this, it looked like a periodic table. You got any of you guys did chemistry? Doesn't it look like a periodic table? It's not. All right. So abstraction is removing all the stuff that we don't need for the processing that we're going to do in this situation. So we only have the relevant information. So hopefully you'll remember this. Remember, I spoke to you about this. Remember the Rotherham subway system? The actual map of Rotherham is quite complex. The abstract map that you'd see on the metro is much more simple because it has all the information that we need. It doesn't have information that we don't need. Like, this is an industrial area. This is an area with a lot of streets in it. This is an area which is open. It doesn't have that because the people who are using the metro probably don't need to know that to get from one station to another. They just need to know where the stations are. This is a real metro as well. This is for Washington, D.C. A lot of cities have metros. And you see they have the lines. So part of the abstraction there is to make it easier to use the abstract model is we coded a bit, right? So they coded this one with lines. They've done that in Qatar with the lines as well, red, green, that type of thing. Any of you guys ride the metro? Yeah. Is it good? My daughter rides it. She says it's all right. So here's another map. Now that looks like the state of Virginia. Yes, it is. There's Richmond. So that's in the United States. The state of Virginia, that would be useful for anybody who worked in the government of Virginia. It would also be useful for anybody who wanted to drive around Virginia. And so some of the things that would really help the drivers would be things like these shield bars there. They indicate that that is a interstate or major road. So if you want to get a place quickly, you'd take those rather than these other ones. If you're like me and you're like a tourist type person and you like to enjoy the countryside, you'd probably avoid those ones and go for these little ones, right? And each of them has a number on it. So, and that maps to, as you drive down the road, you'll see the number. And that's the same in Qatar, isn't it? I mean, you get on the road and it's got, the numbers of the various roads. Here we go. So it seems like we like Virginia, but this is a weather map. And again, if you lived in one of these places, it might be nice to know that there's a little bit more rainy here at Richmond than it is out here at Abington. And, if you know what the prevailing weather pattern was, which in most places is it goes from west to east, you could sort of maybe plan your day around that kind of a map. Okay, so maps, they are abstractions of physical things. And, we put on the map what is useful to us. There's a lot of things missing from that map. It doesn't really show the mountains, does it? No, doesn't show mountains, doesn't show forests. There's a lot of stuff that isn't shown, but that's not necessary for us, right? For the people who are looking at this map. There might be some other people who want to do camping in mountains, and they would get a map that did show where the mountains were. You could get a topographical map. So depending on the use, will depend our layer of abstractions. And these other things we did talk about, we can abstract information. So we have information about things. We can call them entities. And so then we can have properties about those entities. Each entity has a name. Each entity has a value. Each entity has a type. It could be a number of integer, float, or it could be something that you'd represent by a word, in which case the type for it would be a string. Okay, so here is an abstraction of movies as an area of interest. And so the entity here, the thing of interest, the thing is the movie. And so a movie has a title. A movie was produced in a year. So these are one-to-one relationships. Remember we talked about one-to-one versus many-to-one relationships? All of these things are one-to-one relationships. That is, for any particular movie, it only has one title. It was only released in 1 year. It has only one length. It has one genre. I don't know how you say that, genre. It has one format. Oh, it might have multiple formats, really. And it has a price, and that might change as well. Then we see that the instances relate to different movies that all sort of fit that pattern. Now, the idea of layering abstractions, the idea there, remember, is that we can remove layers or we can add layers depending on the amount of information that we need. And so if we need less information, we're having a bare bones sort of abstraction, we can sort of remove layers or add layers to obscure things. If we want more information, we can drill down a bit, and as it says there, peel off some layers of abstraction. And yeah, I already talked to you about this one, the email application. If you go down to this level here, we've got quite a very abstract sort of view of electrical pulse, of just zeros and ones, which actually represents the thing above it, which represents the thing above that. So we've abstracted it quite a lot. This diagram, just to remind you, because we have talked about this before, this diagram, the idea was you have a situation where somebody has designed a system and they abstracted it to a certain level. And maybe the level was that we just have the level of vehicle. But then it turns out that somebody is interested in a particular type of vehicle and we don't have that information. That means that we've abstracted too far. And so then we have to sort of, as we say, peel back that and leak. We allow the abstraction to leak through the layers. If we don't have enough detail, then we might have to go back and actually redo our model to have a little bit less abstraction. In that case, we know that people want to differentiate the types of vehicles. They don't want to just say it's a vehicle. We want to know if it's a van. And so we have to go back and redo our model. And as it says there, some details are missing. And so we need to amend it so that we get all the details that we wanted. Modeling is a subset of abstraction. Now, this one we did talk about a bit, didn't we? We use all kinds of models in computational thinking, and including very visual models that we can see, like our flowcharts, our data flow diagrams, etc., use cases, etc. So here is an idea of a model. A model represents some part of reality, but there's a lot of things that it hides. Okay, so this diagram again, this slide again, we did talk about this before, and this relates directly to a concept of data modeling, right, or data analysis. And actually, a few of these slides have. So I've already mentioned this concept of an entity. There are relationships between the properties of entities and between entities. If you have one-to-one relationships, then that could be something which relates to a single entity. If you have many-to-one, then you've probably got two entities involved. So properties are the information that we store about a particular entity. So for example, your name, your student number, these are properties that we would store about the entity of a student. So a student has a one-to-one relationship with their name. A student has a one-to-one relationship with their student number. On the other hand, yeah, there's some other things that we store. We store their the types of data. Student number is a number. Student name is going to be a string. And any rules that we have about how those relationships work. Okay, yeah. So these slides are going longer than I thought. So static models, we create the model and that we put it out there and it's there, it's just in that mode. Whereas a dynamic model can be affected by events. And you will notice that if you're going to do programming, visual programming, or if you want to say object-oriented programming, you have events. So you write into your code things like click, on click, do this. And so you have events. And so the model changes depending on the state. And we showed that with the turnstile. Remember the turnstile? The turnstile could be either locked or open. And if we insert the coin, it'll change from locked to open. If we go through the turnstile, it'll change from open to locked. Do you remember this one? Königsberg. So this is revision, so I don't want to spend too much time on it. But remember, the fellow made a map which was much, much simpler than the map that he was given. And from that map, he abstracted it to only have the things that he was interested in, which is the different, I guess you said, they're almost like islands, but different places or geography places in that city that are separated, and then the bridges between them. And from that, he was able to answer the question, you know, can we touch all of those islands or places going across the bridges once and once only? And there's a map of the world. The idea here is that you can have modeling which is really complex. I mean, this is so complex, climate modeling, that it's the subject of some debate, or it was until like the last couple of years. They've got sort of come up with a consensus, but they're still working on the models to get them more accurate. There's a lot of things going into this model. So you know what I mean? The model that they use for projecting the climate over years, decades. So in order to do that, they have to get a lot of historical data. You know, so what were the temperatures time ago, and how can we know that? Well, there's a lot of really complicated chemical data that needs to come out of that. They do ice cores, and they measure the proportion of oxygen 18 and oxygen 16 in the ice. I mean, you know, it's not just sort of stick your finger in the air stuff, right? There's a lot of sort of measurements they're doing. They're measuring the chemical composition of the water in the ocean, and of course the temperature at different depths. And from that, and a lot of observation, they can create quite complicated computer models that will, and then they test those models. They'll say, okay, so based on this is what we think is going to happen next year, and then they see how it happened next year, which, you know, becomes this year or last year, and then they test that against the model. And if it doesn't work, then they'll do some tweaking. And yeah, so they've come up with something that actually made them really quite worried, doesn't it? Right? They call it climate change or global warming or whatever. But that was based a lot on models, a lot of measurement and a lot of modeling. This is the kind of last thing that I think we spoke about last time, maybe. But remember the one-to-one relationships between the entity here and all of the properties of that entity. But we've got one property of that entity which is not a one-to-one relationship, and that was that the student could have multiple phones, in which case we would have to modify the table structure if it was a relational database. And yeah, I'm not going. This isn't a relational data modeling course, but if you do one, you'd see that these things could all be one table, but this would have to be separated out in another table. Still going on at this. What do we got here? The credit card. This is a process that is being modeled. And so this is one of those dynamic ones, right? So depending on what happens here with the credit card, depends on, yeah, these other things here. And that's that. Right, so there is, did I go through the thing about wing? Because I'm really making this big today, huh? We're going to run out of time, but what I'm going to do is I'm just going to, I think I'll close this one. And there was another one just there about wing. I'm not sure if did we go through this last time? Maybe we didn't. Computational Thinking by Jeanette Wing. So the idea here is I wanted to sort of entice you to read the article, recognizing that a lot of people won't. So I made some notes about it, but hoping that you will. So this is just a summary of an article which I've made a link for you. And the article was written by Jeanette Wing, and Jeanette Wing was trying to make a definition for this term computational thinking. And so basically she's saying that computational thinking is these things: solving problems, designing systems, understanding humans. So it's not just about like trying to think like a computer. It's not actually thinking like a computer. It's about thinking like a human, but understanding how we can adapt that thinking so that it'll work, it can be applied onto a computer. Mental tools, attitude and skill, courage to scale on to bigger problems. So we know lots of things that computers do better than people. What they do better than people is things that require speed, because computers can work at billions of cycles per second. There are some things that humans do better at the moment. And I suppose when we get to the point where, and this is when, if we get to the point where computers can do everything better than humans, that would be like the movie that you may have seen, The Terminator, I don't know, and they refer to that as the singularity. I mean, so when we get to the point where computers can, they become self-aware, right? So supposedly. Humans are emotional beings as well as rational beings, and perhaps more emotional than rational. And so computers don't really do that. Though some people in artificial intelligence field have said that there's something kind of like that in computers. I don't know. So yeah, so what do we do with computers? That is computational thinking. We have an instructions set. We put some resources, and we work in an operating environment. These are some things that we can do to take a problem and then apply it to a computer. We may have to use, I remember in an earlier lecture, I mentioned to you the two different types of logic, which is deduction and induction. And so where your deduction is where you have facts that are totally related to each other and from which you can draw conclusions. And yeah, that's great for computers. Computers can do that because that's very binary sort of activity. But when you have things where we're drawing approximations, that would require inductive reasoning. And we can do that. And so we have random number generators. We can do this with computers. We build big databases, and we can use approximations. And as it says, we can reduce large problems to smaller ones. And we can embed some functions as a functionality, a function into a computer, transforming numbers and ideas, etc. Simulators. So simulators, that's how pilots train, isn't it? You know, at least half of their training is sitting in front of a simulator, because it's way too expensive to go flying around in airplanes with people who don't know how to fly them. So they start off on a simulator, and simulators are quite powerful. They can put all kinds of sort of scenarios in there, and you know, if you crash the simulator, it's okay. You walk away, and it doesn't really cost anybody any money, and you live, which is also a big benefit. I showed you a minute ago the Fibonacci series. Remember that? Fibonacci series will introduce you to the idea of recursion. And so recursion means where we're doing the same, we take a big problem, we break it into smaller things, and we eventually get to something that can be repeated and within itself, and that's recursion. And so that's a way of thinking. We can solve the Fibonacci series with a computer program, which has about 7 lines to it. You know what I mean? And so we can end up with, I don't know, we can go on to basically as big a numbers as we want for that. Now, the word heuristics has a positive and a negative meaning, but basically heuristics means things like rules of thumb or sort of intuition that you have, where you sort of, just based on your experience, you would do things this way, which isn't really sort of, there's no direct lines. Instead of direct lines, we've got sort of curvy lines between things. So what we mean by that is that, yeah, it's just sort of fuzzy logic, I guess you'd say, would be heuristics. We do use that in our development of our systems, and because of the uncertainties that are involved. And with heuristics, if we have enough data, you can tease out of the data, you can find relationships that you wouldn't have seen. And that's certainly the idea behind big data. Artificial intelligence sort of builds on that. The big data thing this really, it's been with us for a long time, but sort of big data. So Facebook says, I read an article about this about Facebook. Facebook says that based on your Facebook activity, they are able now, they think, to predict your political views, your personality, just based on your Facebook. Now, maybe that's why young people don't use Facebook. I don't know, but basically they say that they can do that. Now, even if you'd say, oh, well, that's easy. You know, we'll just read their political posts. But you might have somebody like me. I don't ever post anything political, right? But still, Facebook could tell a lot about my political theory, about my personality. So one of the things about personal personality, one of the things I say is that your personality is kind of like the average of your 5 closest friends, and they might be family. Right? So you might say, well, why would that be? I like to be with people who are different from me. Well, not really. And what we find is that people with their close friends, their 5 closest friends, they tend to have similar interests. But the other thing is, if they stay together as a group of 5 friends, they tend to pick up the traits from each other. And so that's why they say that, you know, your personality is going to be like the average of your 5 friends. Some of that's just because you select people that you're attracted to friend-wise, that have similar interests. And the other is because you sort of learn from them. So Facebook knows that. I mean, you know, they know who your friends are, right? And they know what their attitudes are. And from that, they can sort of get your attitude. Yeah. So the other thing is that you'll know this because not just Facebook, but like Amazon, they know what ads to give you. I mean, that's why Facebook does this, right? It's everything there is about money. You know, it's about money. Why does Facebook do that? Because they make money by selling